Welcome back to Boiler Wild. My name is Eric Johnson. On this podcast, I talk about boiler industry topics as well as personal development. I have a good one for you today. Hopefully, you think it's a good one. I think it is a good one. I think it is very important to know, especially if you work with a lot of commercial buildings. And I want to talk about expansion tanks. But before I get there, I want to thank everybody who has reached out to me saying that they listen to the podcast. I don't have any names in front of me right now. I forgot to pull those up. But I've had a couple people reach out in the last couple weeks, and I will find those and talk about them on a later podcast. And I want to thank everybody who has rated the podcast 5 stars. That helps other people find the podcast and lets all the podcast platforms know that the podcast is actually of some value and not just data being uploaded. And so that when you search for boilers or Boiler Wild, it will suggest my podcast because this is kind of weird, but the boiler industry doesn't have a lot of podcasts, but so you would think, oh, well, a boiler podcast wouldn't have a lot of competition online. Well, on the podcast platforms, podcasts about Purdue University is actually the competition. So if you don't know, Purdue University, their mascot is the Boilermakers. So there's 30 or 40 podcasts about like boiler, whatever, but it's all about like Purdue athletics and Purdue University. So that is actually the competition, not other people in the boiler industry. So I am just trying to be found among them and trying to stand out, and ratings really help that, and it lets the platforms know that I exist. Once again, trying to be consistent with the upload. So this one will be this week, and then I'll have another one closely related for Thursday. So listen when you can and let me know. Please reach out if you have questions, if you have suggestions, or you just want to talk. I always love talking and meeting with new people. And yeah. And if you want to be on the podcast, reach out too. We can make that happen if you have some industry experience or want to tell some stories about whatever. There are no rules. The only rules are have fun and education. So, expansion tanks. What is an expansion tank? An expansion tank is a tank. Yeah, you can't use the word in the definition, but the expansion tank is a tank or a vessel in a hot water system. And by hot water, I mean non-potable water. This is heating hot water system. I guess I should be more exact. Heating hot water system. Although they do have expansion tanks in potable water systems for like domestic water, I am specifically talking about heating hot water systems, non-potable water. But the expansion tank works the same way, but they're just applied slightly differently. And yes, but the actual tank is basically the same. Anyways, an expansion tank is a vessel that allows water to enter the vessel, and it uses air as a spring, as a cushion. So we all know, hopefully at this point, that water is not compressible. So if you try to compress water is a fluid and it does not compress. So then the only thing that goes up is the pressure. If you try to press it down, that is how hydraulics work. Only they use oil or hydraulic fluid to move cylinders in and out, because if you apply 400 pounds of force on one side of a cylinder, 400 pounds of force comes out the other side of the cylinder. But in a heating hot water system, an expansion tank allows water to push against the air in the tank that acts as a spring. And why would water be pushing against that vessel? Well, when water is heated from any temperature to a higher temperature, it expands in volume. And this volume change happens because the molecules of water get farther apart and start moving more rapidly. And that's essentially how water behaves when it gets heated. So when you fill a hot water system, let's say it's going to be 50 degrees coming out of the ground. That's pretty normal for most of America, 50, 55 degrees. And you are going to heat it to 180 degrees. So you have that differential of temperature, and that differential temperature, the volume of the water at 50 degrees is going to be different than the volume of the water at 180 degrees. And that difference we have to put somewhere. And we could either put it down the drain every time we heated up the system. So we would have extra water and we would drain it out. That extra water would then be a waste because every time we would cool the system, we'd have to add water. And that would also induce a lot of outside particles and oxygen into the system. So we definitely don't want to do that. We want a closed system. So what we came up with is called an expansion tank. And the expansion tank, once again, has a trapped air bubble inside of it. And the water can push against the air and act as a spring, and the air will push back, but the air will be able to be compressed. And there are 3 types of expansion tanks. You have a compression tank, you have a diaphragm tank, and you have a bladder tank. A compression tank is old school. This is what you're going to find in the 1950s church that has cast iron boilers if they don't have a steam system, or like an old school system. This is, you're going to look up in the ceiling and you're going to see a 4-foot by 8-foot tank in the ceiling and be like, oh, look at that thing. That thing's giant. Or maybe they retrofitted the boilers and just left the tank in the ceiling. That also happens often because the tank is so large. But a compression tank is just a cylindrical tank and has nothing inside of it. And it works on manually setting the water level of the tank in order to provide the air cushion. So how that works is you would have your entire heating hot water system, and you connect your air separator or your top of the system, maybe above the boilers. You connect that point so that any air that reaches that high point can then slope up in and keep sloping up in towards your compression tank. And then the air goes into the compression tank, and then the air bubble keeps moving up and will go to the airspace in the top of the compression tank. This allows the system to move air into the compression tank and also allows a cushion of air to push back on the water. So when the water gets heated up, that air cushion is trapped in the top of the tank and will push back on it. There is a special fitting that goes on the bottom of a compression tank, and it is typically called an air troll fitting. That is a industry name that is trademarked by Bell and Gossett. But it is a special fitting that has a tube on it, and that tube essentially helps separate the air and water in the tank and allows air to directly enter into the tank and enter into the airspace versus entering into the water. But the major downsides of these tanks are they have to be larger than other size tanks. So since the air is initially not compressed, I'll go over on setting up a compression tank a little bit more in depth, but you initially cut in the system and have about a quarter amount of water in the compression tank, and then you start heating it up. And when you heat it up, the water volume in the system expands, and the water is going to expand in the tank and ends up being about halfway, maybe 3/4. And the trapped air, since it has a lower volume, will increase in pressure. And that is how a compression tank works. The major downside of a compression tank is, one, they're larger, but two, they are very maintenance heavy. And by that, I mean they lose their air charge or their air area inside the tank pretty often due to leaks. And the leak will either come from the sight glass. So in order to know where you are on the level of the tank, they will typically have a sight glass. And a compression tank is typically, I don't think I've ever seen one that's vertical, but it's going to be a cylindrical tank installed in the horizontal position, and it's going to have a sight glass on the one side with two tappings. And that sight glass is going to show you the level in the tank, and that's how you set the level of the tank. However, even though you believe that there are no leaks on that sight glass, over 24 hours a day, 24/7, tiny, tiny little amounts of air can slip out of the top parts of that sight glass, and that can slowly bleed off the air charge of the tank. So that is why when you have a compression tank, you are supposed to set the level of the tank with the sight glass, and then you are supposed to close the valves to help prevent the loss of the air charge, which will also mess up people if they don't realize that the valves are closed and they think the tank is halfway full when it's really 100% full. And they need to open up the valves of the sight glass in order to see that the tank's full. The other way is air redissolving back into the water and then that getting passed out back to the system. As water is heated and cooled, it basically accepts a certain amount of dissolved oxygen. And when you heat and cool a system, air will get pushed out of the water. And then if air is still allowed to touch water and you cool the system, that air will get redissolved back into the water. And that will slowly remove the air cushion or the air bubble that is in the top of a compression tank. And what ends up happening is basically once a year or the start of every heating system, you need to reset the tank, and it becomes a major pain. And you can also get some intermittent service calls, especially on customers that are not too financially sound and are just dealing with an old system. And maybe they have a leak or maybe they have air issues in their system. And a compression tank, I have never seen one work exactly how the books write it up and envision of all the air in the system gets captured and put up to the tank. The major issue with that is the tank essentially has to be the highest point of the system above a certain point. So that is why you will always see them up in the ceiling of a boiler room and not sitting on the ground next to the boilers. But with modern day technology, everybody loves to install air bleeders, automatic air bleeders in a system, get the air out. And when you do that, you will lose all your air in your tank due to the air redissolving back into the water and coming out of the tank and then getting removed by the automatic air bleeder. And then you will lose all your compression air in your compression tank. And now your system will overpressurize and your relief valves will start leaking. That's another note I should cover now is compression tanks. You are not supposed to have your automatic air bleeders open if you have a compression tank. You can open them up at initial system fill, but once you commission the system and turn the boilers on and heat it up, you want to close off all automatic air bleeders. All air needs to be routed to the compression tank in order for the compression tank to work correctly. Well, that was a long explanation for compression tanks. So what are the other two? We have diaphragm and bladder. So the three types of tank: compression tank, diaphragm tank, bladder tank. The second one is diaphragm tank, and it is exactly how it sounds. It is a tank. It is a cylindrical vessel that has a diaphragm in it. The diaphragm is attached or fixed to the sides of the wall of the tank, and the tank is built around it. They are non-serviceable. So you will have air on one side and you will have water on the other side of the diaphragm. And on the air side, you'll have a little Schrader valve that you can add air or remove air to that side of the diaphragm. And on the other side, you'll have the water connection that you can obviously attach to the system. Diaphragm tanks are typically used for cost. If you have a smaller system, they are more cost effective than a bladder tank. They're also not offered in large sizes as a bladder tank. So a residential hot water system will typically use a diaphragm tank. A light commercial system that's maybe 2 million BTUs, you could probably get away with a diaphragm tank. I believe the limit of the manufacturer was 200 gallons of partial acceptance of the tank, and I'll talk about partial and full acceptance a little bit later. But a 200-gallon tank is not super huge for a large commercial or industrial system. So then you would want to move to a bladder tank. And a bladder tank, I believe, is the best of all three. And I will tell you why. So a bladder tank, once again, cylindrical vessel, however, is going to have a flange or some kind of service opening where you can add or remove a bladder. A bladder is a thick rubber balloon that is attached to the flange or the service opening of the tank, and that is where the water connection goes. The water of the system goes inside the bladder, so water is inside that bladder and will then expand the bladder as the pressure increases. The air is between the inside walls of the tank and the bladder, so the air pushes on the outside of the bladder. The air and the water in a bladder tank do not touch. Once again, and I confused this for a while, the water in a bladder tank does not touch the tank. It does not touch the air. It only touches the inside of the bladder. And a bladder is just a thick piece of rubber that manufacturers make, and then they slide it, they roll it up real tight, and then slide it in through a little opening in the top of the tank, and then it can expand. But the water only goes inside the bladder. And as the bladder fills up with water, it expands inside the tank. But since the air between the outside of the bladder and the inside walls of the tank is trapped, that provides the spring or compression to push back on the bladder, but also allow expansion of the bladder. But as the bladder expands, the air pressure is going to increase. However, if you have a bladder tank and you have water, and I would say system water, so sometimes you can get condensation in a bladder tank in the bottom of the tank, but most tanks will have a drain. And if you open it up and you're getting system water out, you have a leak in your bladder, and the bladder needs to be replaced. But if it is a small enough tank, it may just be worth it to replace the whole tank. Depends on the age of the tank, depends on how easily the tank can be replaced, and or if you can get a bladder for it. But most often you're going to replace the bladder. But a bladder tank, I believe, once again, is the best of them, and that's what you should always install. So next part of it is ASME versus non-ASME. I don't know all the local codes and restrictions. You can install a non-ASME tank, and by non-ASME, that is, so ASME, Boiler and Pressure Vessel Code, Section 8, I believe, is the one for pressure vessels, which governs expansion tanks, and that is going to be non-fired pressure vessels. And the tank will either just be built by a manufacturer and just have their name on it, or an ASME tank will be built by a manufacturer, have their name on it, but then also have an ASME number on it and like the ratings. And that data stamp is required in a lot of commercial industrial buildings and over certain sizes of BTUs or water volume. I am always of the opinion of no matter what, unless you're really, really competing on costs, the only downside of ordering an ASME tank is the tank is going to be more expensive than a non-ASME tank. But if when in doubt, buy ASME and you can't be in fault. So there are non-ASME tanks out there that you can use for commercial purposes. But if I was a contractor, I would always buy ASME unless you really knew that the budget for the job was tight and you understand the local codes and building codes and everything that they don't require ASME under a certain size of the system. But when in doubt, buy ASME and you'll be safe. So, and I mentioned this previously, full versus partial acceptance. So full acceptance is a bladder, and I'm talking about a bladder tank here. Bladder can expand to fill nearly 100% of the tank. So if you have a 100-gallon tank, it's going to be a full acceptance tank is typically going to take around 100 gallons of water. Partial acceptance is a 100-gallon tank will not accept 100 gallons of water, and this is typically done with a diaphragm tank because part of the tank is going to be air no matter what, because the diaphragm can only move so much. So the diaphragm is attached to the inside walls of the tank, and it can only flex so much. So a 100-gallon tank may only accept 70 gallons of water. So if you spec a 100-gallon tank and you need 100 gallons of expansion volume, and you buy a diaphragm tank that only has partial acceptance and it has 70 gallons, well, your system pressure is now going to rise above what you want because you don't have the extra 30 gallons of expansion volume that your engineer, your drawings calculated. So just keep that in mind when ordering. That is typically called out on the cut sheets of expansion tank. Now you may be wondering, how do I size the expansion tank? So there is math to it, but as all manufacturers do well, they like to make math easy for us. So Taco, Amtrol, Wessel's Company, Bell and Gossett are the expansion tank companies I looked up, and they have expansion tank sizing. So you would just fill in the fluid, which is water or a ethylene glycol or propylene glycol. That makes a difference because if you add glycol to the system, glycol will expand at a different rate than water, and you will need a larger tank than if you had 100% water system. So if you have a hot water system with glycol added, you will need to calculate for a larger tank. Keep that in mind. If you're adding glycol to an existing system, you may run out of expansion volume inside your tank. So then you have system volume, and then that is going to be essentially how much water is in the system in gallons. And you're probably asking yourself, well, how do I calculate that? You can either do it by looking at the drawings and doing some rough estimates of the piping. You can do it by looking at all the mains of a building. You can do it off a rule of thumb of ETUs of the system. You can do it off of the existing tank size, and that would just be a like-for-like replacement. If you have that, if a tank has been working and there seems to be no issues, you can change it like for like. But typically for an existing system, you're not going to have drawings, and you're obviously not going to be able to measure all the pipe, but you can look at the mains and get a rough estimate of the volume of the system from what you can see, and then you add a safety factor to that. And the most accurate is when you initially fill a system, you have a water meter or a temporary water meter, and you clock the meter, and when the system is filled, you write down that number, and that is your volume. However, at that point, you will typically, on a new job, already have the expansion tank installed. So hopefully the engineering firm designed the system correctly and designed the expansion of the hot water tank volume correctly. But that is if you are maybe filling up a system on an existing building and don't have the drawings, you can look at the water meter and fill it up and write that number down for any future use or purposes. Or maybe if you got to finish up a retrofit and you weren't sure on the expansion tank volume, you can fill up the system a little bit more before heating season, get an expansion tank, install it, and then start up the system. So the next criteria is the minimum initial fill or operating temperature. This is typically going to be between 45 degrees to 55 degrees, depending on where you are in the United States. This is just a guesstimate. When in doubt, go low. Typically 50 degrees is good enough. The ground or earth is going to be between 50 to 55 degrees. If you're in Florida like me, it's going to be a little bit warmer in the summer on most days. Like if I turn my shower all the way cold, the temperature of the water is warmer than if somebody in Minnesota turns their shower on all the way cold in the winter. But it's not by much. In Florida, it may get up to 60 degrees when everything is cold. But if you just use 50, that's good enough. Then you have the maximum design temperature. So this is going to be the maximum temperature that the hot water system is going to be operating at. And I would typically add a little bit of safety factor here. So if you say, well, the system is going to be operating at 180 degrees, great, that is operation. So the system will probably shut down at 185 to 187, maybe 190. So I would use 190 or 200 for that. You can also do the maximum temperature for the boiler, which is 210. But if you're really condensing and your maximum system temperature is going to be 100 degrees, you can add a little bit of safety factor for that, but maybe you would type in 140 to the sizer. The only downside is if you type in too large of a number, you're going to get a much bigger tank than what you need, and all you're going to be doing is paying more. If space is an issue, obviously the tank is going to be a larger size, so typically it's not going to change too much, but depending on the size of the system, like if you're working on a giant hospital and your expansion tank is 1,000 gallons and you have two of them, you're going to want to be pretty dead nuts on your calculations versus you have a teeny little school and it says you need a 150 gallon tank. If you order a 200 gallon tank, it's not the end of the world. And then you have the initial fill or operating pressure. This is going to be what the pressure of the system is going to be. And this will change based on where the tank is located in the system. Most buildings are going to be 1 to 2 stories, going to be pretty flat, and the boiler is going to be on the first floor. However, if you get into apartment buildings, if you get into taller buildings and the boiler starts changing and the location, whether it's in the basement, the middle, or the top floor, that is going to change the system pressure of what the expansion tank sees. If you have a 40-story building and the expansion tank is located on the top floor of the system because the boiler room is on the top floor, the pressure is going to be about 10 to 12 psi there, but at the base of the system, it's going to be, if it goes all the way down, it's going to be like 80 psi, something like that. So if you have the boilers in the basement of a 40-story building, now the expansion tank is going to be seeing that 80 psi, and because all the weight of the water of the entire building, the water has weight. So when you initially fill the system, if you're filling it from the penthouse, from the top of the system, that water weight is going to be pushing down on it. But if the expansion tank is at the top of that system, it's not going to see that 80 psi. So you don't have to design it for that 80 psi. But it would probably be a good idea to make sure that your expansion tank is correctly sized with the maximum pressure and not like right at the limit. Typically they're in steps, but you got to keep that in mind, especially if the mechanical room is midway through the building, because now you're going to split your pressure in half and it's only going to see really the pressure above the tank and not below the tank. So you got to keep that in mind when you are sizing it and also when you are calculating your fill pressure needed for your building. And then the max design pressure of the system, typically that's going to be 160 for a hot water system, but it could change depending on what you have. But Section 4 hot water boilers are designed for a temperature of either 210 or 250 degrees at 160 psi. Then this Take One has connection options, standard NSF certified stainless steel flow through, and then anchor clips and sight glass, yada, 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 whatever. But if you plugged it all in, it would tell you what you need. The Amtrol, once again, has the same exact calculation. It's going to be all the same. The math is the same through all the manufacturers, but every expansion tank manufacturer will have a calculator on their website. Use them because it makes things easy for their selection because they will tell you exact model of what you need. But you got to have good data, garbage in, garbage out. So make sure you are feeding it good data. Where do you install the expansion tank in the system? You are going to install it on the suction side of the pumps. And I will talk about this in another episode, but the expansion tank is called the point of no pressure change. And this is a whole episode in itself, but you always want to be pumping away from the point of no pressure change. So if you walk in and you see a system where the pumps are pumping towards the expansion tank, so you have the boiler and then you have the pump and then you have the expansion tank installed, you're pumping towards the point of no pressure change, and that is wrong. Dan Holohan wrote a great book on this, Pumping Away. You should read it, but I will also explain it in a podcast at a later date. So stay tuned. Come back for that one. But if you remember nothing, just always remember pump away from the point of no pressure change, and the point of no pressure change is the expansion tank. So if we are installing a bladder tank, and I'm going to go over the installation of a bladder tank because I believe that one's the best, and I like it the best, and I like the serviceability of it, and I like the full acceptance volume of most bladder tanks. Just makes it easy. Yeah, they may be a little bit more expensive, but what's money? You're just spending somebody else's money. Isn't that right? When you install a bladder expansion tank, the number one issue that I see is no serviceability. And by no serviceability is you can't even set it up correctly. When you order the tank, the manufacturer may or may not give you an option to have the air charge set. Some manufacturers will change the air charge. Some will just ship their tank at 12 psi or 40 psi, no matter what, and then you have to change it. So if your tank shows up at 40 psi and your system pressure only has to be 20, and your contractor cuts in the tank and they say, hey, we're popping our relief valves are only good to 30 psi, they must be bad. Your brand new relief valves on your 3 boilers are leaking. That's a warranty call. So call the boiler manufacturer rep out here and get them 3 new relief valves because all 3 are leaking, because these valves, they're junk. They don't make things like they used to anymore. Well, when I hear stuff like that, you have to go, really? All 3 relief valves on brand new boilers are just leaking at the same time? What is the system pressure? Oh, well, the system pressure shows 30 psi. Oh, that's weird. So when we heat the system up, the system pressure gets to 30 psi and then the 30 psi relief valves start leaking. That's almost like what they're designed to do. What's the pressure in the expansion tank? Oh, well, that's whatever the manufacturer set it at. In that case, 40 psi. So pressure is pressure, and water cannot push magically against a higher pressure. If the pressure in your bladder tank is 40 psi, in order to start expanding that bladder, you have to have 41 psi of water pressure or more. So you have to properly set your expansion tank air pressure to what your system pressure is. And sometimes you can set it exactly at the system pressure. Sometimes you can set it a little bit more, but I typically would set it at the system pressure, the calculated system pressure plus a 4 psi safety. So let's just say that is 20 psi. So the contractor's already cut in the tank, and you talk to him over the phone. You're like, hey, you got to reset the air charge on the tank. They're like, oh, okay. So then their plumber or pipe fitter, whoever goes out there, and they bleed off the air charge till it says 30 psi. And then they call you back and say, hey, the 3 relief valves are still leaking. We think they're bad. Like we initially told you, idiots. You never listened to us. You need to come change them because they're leaking water all over this brand new boiler room. And it's causing a mess, and we're losing a lot of water, and we're trying to heat the system up. And every time we get to 140 degrees, the relief valves start leaking. So then you say, oh, what is the system set at? And they say, well, the system pressure right now is 30 psi, but it's supposed to be 20. And you're like, oh, okay. So why is it 30? So then they go back to the engineer and they do all this roundabout stuff. And they say, well, we set the air charge on the tank. We lowered it now to 20 psi. Okay, great. And how do you know it's 20 psi? Well, we removed air from the expansion tank until the air charge said 20 psi. Did you remove the water from the tank and allow the water to go to atmospheric pressure? No. Why would we do that? And that is the number one issue is, so if you have a bladder tank and you are trying to set the air charge, you cannot have water pressure pushing against the air. It will just display the total pressure of the water and the air. So if you have a tank and it is 95% full of water because the bladder is expanded all the way, and you check the air charge and the air charge says 30 psi, and you say, oh, we're supposed to have 30. Great. That's what we need. Actually, let's go back. I'll just make it the same with the example. So then you check the air charge and it says 20 psi. You're like, great. That's what we need, 20 psi. But that's because the system is actually at 20 psi and the water is pushing against the air and it's equaling 20 psi. However, if we were to let the water out of the tank, cut it out from the system, and let all the water expand or get removed from the tank and let the air expand to zero pressure, we would then see the pressure of the tank drop because the water was taking up most of the volume of the tank instead of the air. This is important because we would only have, in that case, 5% of our expansion volume when the tank was set at 20 psi. The proper way to set a bladder expansion tank is the water side of the bladder, so the side that is connected to the system, has to be at atmospheric pressure. If you have water pressure pushing against it, you cannot set the air charge. If you measure the air charge, that measurement is a lie. That just will tell you the system pressure at that point. It will not tell you the actual air charge of the expansion tank. So what do you got to do? You got to remove the water pipe. So typically people will miss a union or way to remove it. So then you have to just cut the pipe. And typically it's a copper pipe. So they're like, oh yeah, we'll just cut the pipe. So then they cut the pipe and 50 gallons, 70 gallons of water comes spraying out everywhere and make a mess of the brand new room. They're like, oh, that's a mess. It's because the water is pressurized from the expansion tank, from the air that's trapped in the tank, and will push on the bladder until everything neutralizes. So it's going to push a lot of water out of the tank, especially if the tank is a larger tank. So that is why Bell & Gossett and other manufacturers sell a specialized tank purge valve for non-potable water expansion tanks. It is a specialized valve that combines three functions in one: a ball valve, a 5/8 inch drain, which is just your standard hose connection with a little ball valve on that, and a union. What the union allows is the union gets connected to the tank. So if you need to remove the tank, you can remove that union, and the ball valve is upstream of that union, which will isolate the tank from the rest of the system. However, you can also close that ball valve and then open up the drain valve and attach a hose to the 5/8 inch hose connection, and you will now be able to control the water flow out of the tank and send it to drain, or recapture, or whatever you want to do. But you'll be able to drain the tank for maintenance and service, or checking the air charge in a controlled manner. These valves are not expensive, although they do require some forethought because you have to order them before you install the tank. You can also just use a ball valve and then a T with a drain connected to the T and then a union under that. It's a little bit more work, but it will work as well. But you have to have a way to remove the tank from the system, which is going to be typically a union. On a larger system, it'll be a flange. Then you need to have a drain. The easiest drains are 5/8 inch garden hose connections, and then you need to have a way to isolate the tank from the rest of the system, and that is going to be a ball valve. I have seen many bladder expansion tanks installed with no isolation valve between the tank and the system. I've also seen them installed with the isolation valve, but no way to drain it. So then you end up either drilling a hole or cutting a little hole, or somebody just doesn't know and they just cut the pipe with a Sawzall, and they get soaking wet because all the water from the expansion tank comes flying out of there real quick. So when you are installing a bladder tank, make sure it's serviceable. Make sure you have that union. Make sure you have a drain between the union and the ball valve for isolation so that you can drain the tank and reset the charge and or replace the bladder without completely shutting off the system and draining the system, or freezing the line and having to add a valve afterwards. This is a major time waste on a boiler startup if your contractor turns on the expansion tank yet did not set the air charge or check the air charge, because you, as the boiler starter person, you are not there to be of engineering assistance, and you're just there to start the boilers. However, you start the boilers, you start heating the system up, and all of a sudden you're popping your relief valves. You're like, what is going on? And then you go, oh, wait, I listened to that Boiler Wild podcast, and I remember him talking about the air charge of bladder tanks. Let me go check that. And the contractor will say, the air charge is 30 PSI right now. Oh, we need to lower it to 20. And they will just bleed out the air from the tank, which your water pressure is 30 at that point. So it's just going to expand more water into the tank. It is not actually going to tell you what the atmospheric air pressure is when the water's at atmospheric pressure. So when you set the tank, the water has to be open to the atmosphere of the room. So the inside of the bladder, which the water gets connected to, open to the atmosphere. And then you pump in 20 PSI of air, and that's going to collapse the bladder down to basically nothing. But then when you start adding water to the tank, now when the system gets up to 20 PSI and it starts to expand, it will expand and push against the air cushion of the tank, and the air cushion will be proper in order to not allow the relief valves to pop at 30 PSI. And another part of sizing the expansion tank is knowing how much increase of pressure is acceptable. If you have a 20 PSI system and you have 30 PSI relief valves, you do not have a ton of room for expansion of pressure. If you have 75 psi relief valves and you have a 20 psi system, you have lots of room. So the larger the expansion tank, the less the pressure change. The smaller the expansion tank, the more the pressure can change. So you can get away with half the tank that you need, but the pressure will rise more than a properly sized tank. So you got to keep that in mind when you are sizing the tank, how much difference between your relief valves to your system pressure, or the pressure where the expansion tank is going to be installed. Now, story time. Let me tell you, back in my good old days of doing some boiler startups, doing a startup for a hospital, let's say it was 6 million BTUs total, 2 boilers, 3 million each. And I dragged my stuff all the way up to the penthouse. And, it was not a huge hospital, but it was decent size. But drag myself all the way up to the penthouse, walk across the roof, walk in, and they're like, "We're ready for startup." I'm like, "Okay." And, this is the initial observation phase. This is the phase of startup. And I don't know if I've talked about this, but I've talked about observation. But on the initial phase of startup, you need to determine, can these boilers be started today? And is there anything outside my control of why they cannot be started today? So I am looking at these boilers, and they are installed kind of in the corner of this mechanical room. And they built this rack in front of the boilers to kind of install like some piping on it. And there's this little 5-gallon, or maybe it was a 10-gallon tank, but I'm pretty sure it was a 5-gallon tank. Little 5-gallon diaphragm tank hanging off the piping, and it was attached to the rack. I'm looking at it, and then I'm looking at the piping, and I trace the piping back to the boiler. I'm like, 5-gallon expansion tank. That's weird. Never seen a tank that small. So then I point to the tank. I'm like, "What's that?" They're like, "That's your expansion tank." I'm like, "Huh? Okay. Seems a little small." They're like, "Well, that's what they gave us." I was like, "Oh, all right. What do I know? I'm just the dumb startup person." But I'm like, I've never seen a tank that small, even on a boiler system with only like 6 million BTUs of input for hot water. Like, this seems like it should be at least like 50 gallons or something like that. Can we see the drawings? So the contractor finds the drawings, flips through the drawings, goes to the schedule, and what do you know? The heating hot water tank is, I think, 50 gallons or whatever it is, and the chilled water tank is 5 or 10 gallons, whatever it is. I think it was 5. And they had mixed up the hot water tank, the heating hot water tank, and the chilled water tank for the loops. There are different loops. They had mixed up the expansion tanks. So on the other side of the room was the chillers, and pretty small chillers. But for the chilled water, they had a 50-gallon tank poured and installed on this nice pad sitting next to the system and everything. And I was like, okay, well, that tank is supposed to be over here by the boilers connected to this system. And this little tank is supposed to be over here connected to this system, because a chilled water system, the water will not expand as much due to there's not going to be as much change of temperature. In a heating hot water system, the water will go from 50 degrees to 180 degrees in a heating hot water system. On a chilled water system, it may go from 40 to like 55 degrees or 60 degrees, whatever it is. But it's just going to go between that 30 to 40 degree delta. And also, as the water is cooler, the expansion of volume is going to be less. So water heating up from 40 degrees to 60 degrees is not going to expand in the same volume as water that heats up from 160 degrees to 180 degrees. 160 degrees to 180 degrees is going to expand in more volume. It's only like 1.5% more, but hotter water will expand in a larger volume than colder water, and that is why those two things are why a chilled water expansion tank doesn't have to be as big as a heating hot water expansion tank. So they flipped the tanks. I made sure that the tank was installed correctly, that it had a drain set, because we had to pump up the pressure because they had set the pressure wrong. They had set it for the chilled system, and we needed it for the hot water system. And so I calculated all that, but since the boilers were in the penthouse, we didn't need the typical system pressure to go the whole height of the system because the expansion tank and the boilers were already at the top of the system. So our system pressure could just be 12 or 15 psi, whatever it was. And at the bottom of the system, it would see 40 or 50 psi, forget the height of the building, but that's what we calculated out to be. But I didn't have to set the expansion tank to 50 psi because the water at the top of the system is not going to be 50 psi. Got another story for you, full of stories today. So I'm doing a startup at a hospital, a little bit larger this time, 30 million BTUs of boiler for the hot water, and they have two expansion tanks. They are probably 15 feet tall, 8 foot wide, probably the largest expansion tanks I've ever seen, two of them. And being the excellent startup person that has been burned by improperly set expansion tanks and my relief valves popping halfway through my boiler startup, causing an entire day of downtime that we can't bill for or fight the bill for because the contractor doesn't want to pay. But the whole thing of it's not our fault, but we're supposed to just give them money for their mistakes. But anyways, I asked the contractor, I'm like, all right, what'd you set the tanks to? And they're like, they were factory set. I'm like, okay, cool. What does the engineer drawings say they need to be set to? And the engineer drawings say the tanks need to be set to, I think it was like 50 psi or something. And it's probably more than that, probably 75. It was a pretty tall hospital. And I'm like, okay. And what are they currently at? And they hadn't turned them on yet, or they had turned them on. Sorry, they had turned on the tanks. So they had to shut off the tanks and they had to drain them. And these giant tanks took forever to drain. But finally they drained out and we got the bladders to atmospheric. And they were set at, I think, 20 psi. So the tanks were basically full from just static system pressure when the contractor had opened up the tanks to the system. So I'm like, okay, well, we need to pump them up to 75 psi. And it took a guy probably it took a guy probably 4 hours to pump both these tanks up to 75 psi using a air compressor. It was probably it wasn't a little pancake air compressor, but it was like a air compressor with a little 50-gallon tank, little mid-grade contractor air compressor. Probably took him about 4 hours of pumping the tanks up, and I gave him my cool snazzy air gun that would attach itself to the Schrader fitting so he didn't have to hold that side of it, and then he just taped the trigger, and it had the pressure gauge and everything. And I said, these were 15-ish feet high. So he was on a man lift and he probably stood there at least 4 hours. And it was a split over the day because I don't know how I remember this so well, but it was the end of the first day or end of the second day, because there were so many other issues but I was starting to, doing my system checks. And I haven't even fired the boilers at this point. I don't care about the boilers on startups. All the system issues are what are going to bite you. But you probably spent 2 hours and then quitting time, and then came in and another 2 hours at least. I believe it was more than that, but just for the sake of this story, 4 hours sounds good. I remember it being forever and it holding me up and me telling the contractor, like, hey, like, I can't just stand around here for you guys to pump these things up. But it took a while. And that air compressor does not have a duty cycle of 100% duty for 4 to 6 hours, however long it took. That thing was smoking hot by the time that guy was done. But we got it done, and we got the tanks pumped up to the engineered design system of what the tank should be. If you don't know, if you have an engineered design system and like, it's not your company just engineering it off of back of a napkin, like actual like engineering firm puts together the system on the schedule, they will show the expansion tank and it will show the system pressure. You should always do a gut check and say like, hey, does this make sense? Sometimes that system pressure may have been copied over from another spec or something, but you should always look at where the expansion tanks are in the system and say, okay, yeah, this makes sense for the height of the system and where they're installed. This is great. So that is why you need to pay attention to expansion tanks and especially bladder tanks. For compression tanks, I don't love them, but they are still in a bunch of old systems. And they are the cheapest tank to buy at first, but I would not recommend it to a contractor. One, because they have to be installed in the ceiling in the perfect point. Two, the air charge, no matter what you do, will always leak out and or redissolve back into the water and slowly get compressed over time, which leads to miscellaneous service calls for your customer, which then they're like, oh, like we're constantly bleeding this expansion tank and doing this and doing that. Seems like every heating season, like, why do we got to keep paying for this and all this stuff? Ends up being a bunch of maintenance. And if they don't take care of their tanks, then their relief valves start leaking. And then the boiler inspector says that they got to change those because now they don't seat or they have corrosion on them. So it just ends up being this big ordeal. And also for automatic air separation, you can have automatic air separation when you have a diaphragm or a bladder tank because the air is separate from the water and you want to get all the air out of the system. However, when you have a compression tank and the air is touching the water and you are just trapping air in the top of a tank, you cannot have automatic air separation. And that just sucks because if you have a leak and nobody's paying attention, one, if you have a leak, it's going to screw up your system pressure and maybe their fill valve, their pressure reducing valve for their fill, the system's not set correctly or not working correctly. And adding fresh oxygenated water adds a bunch of air to the system, especially a little bit over a long time. And that ends up being large air bubbles. And I've never seen a compression tank accurately and successfully remove all those bubbles. And when we have high dollar boilers like boilers of today that are condensing boilers and decently fragile, we want to give them the life they deserve, and cheaping out on the expansion tank or not replacing the expansion tank and putting in a diaphragm or a bladder tank and keeping the compression tank and then not putting in proper air removal will kill your boiler. It will also corrode your system, but if you have air in your boiler, that reduces the amount of heat transfer, can cause overheating at the top of your heat exchanger, and can cause cracking, which is common on stainless steel condensing boilers. So that is what you want to avoid. On any hot water system, we want to get all the air out, and I would recommend a coalescent air separator. A automatic air vent on the top of a T at a direction change is not good enough. You need a actually manufactured air separator, and I believe they may not all be it, but you want a coalescent one, which has a mesh piece in it, and that mesh piece will trap tiny little micro bubbles and will remove those micro bubbles from the water. So get yourself a proper air separator on your system. And most importantly, make sure your expansion tank is installed correctly for service. So make sure you have a way to disconnect the tank from the system while also being able to drain the tank in a controlled manner and also be able to isolate the tank from the rest of the system while you're doing that. So you're not draining the system and doing all that nonsense. If you want 100% redundancy, you can install 2 expansion tanks. Most people don't really need to do that because technically you can get away with it for a little bit if the system temperature doesn't change of not having an expansion tank, because the expansion volume of the system is not changing. So you just need to do service for a day or whatever. Turning off the expansion tank isn't a huge deal, but you got to make sure that the water temperature in the system remains the same. If you're doing a startup or you're installing a brand new expansion tank, make sure for that bladder tank that it is set correctly for the proper air pressure before they open it up to the water. Once they open up to the water, that reading is just the system pressure. It is not the air pressure inside the tank. It needs to be the air pressure without the water connected to the system. The water needs to be at atmospheric pressure so you get the proper reading. So watch for that on your next startup. That will burn time even for a little tank. I guess I can tell a third story, probably 6 million BTU of boiler, not a huge tank, probably 150 gallons, maybe 200. I don't remember, but it was a decent sized tank, probably 5 feet tall. And, I told the contractor, I said, hey, like, we gotta make sure that this tank is properly set. Like, this tank isn't set. Like, you gotta drain it all out, do all this stuff. They didn't have the proper drain connection. They only had a union, so they cracked the union and water went everywhere all around the tanks. They put a rag over the union and, they're trying to sweep water to the drain. Of course, the drain people always make sure that their drains are the highest point in the boiler room. So they finally got it dry, and this is like the foreman that I'm talking to. He's like, oh, like, I'll just use my bicycle pump and pump this thing up. I'm like, you sure? Like, I have an air compressor in my truck. I can get you my air compressor. You might be there a little bit. It's like, I'll just pump it up with this bike pump. I'm like, all right. So he spends 15 minutes doing that, and he then comes back to me and says, hey, you still got that air compressor? He's like, I've been doing that for 15 minutes, and I haven't even seen the pressure go up. I'm like, yeah, you're using a little bike pump on like a 150-gallon tank. It's going to take a minute. Your bike pump only produces a tiny little bit of volume. If you think about pumping up the tube of your tire for your bike, pumping up a little bike tire takes 15 to 20 pumps at least. So I'm like, what do you think a 150-gallon tank is going to take? So I got on my air compressor, got on my fancy fitting that auto connects to the end and has the gauge and everything, makes it super easy to fill the tanks. And we filled it up within a half hour or so. Got it all lined out. Everything was good to go on that system. But yes, make sure your expansion tank is installed correctly. And for service, for maintenance, it's a good idea to check a bladder tank that it's not leaking. So the bladders will break, they will leak. And once the water is now touching the air, you no longer have an expansion tank, you just have a expensive vessel, and you have to replace the bladder. Or you can replace the whole tank depending on the cost of both. But you typically on larger tanks will just replace the bladder. It will be a pain, but you can do it. But once the bladder leaks, all the water will leak into the air part. And when you tap on the side of the tank will have a very dull thud to it. Whereas a typical tank that is properly sized will sound hollow because the bladder is actually suspended in the center of the tank and won't be pushed up against the walls. So the tank or the metal or the steel, when you tap on it, like with a crescent wrench, will sound hollow. That's kind of how you quickly check that an expansion tank is working correctly or not, versus if it sounds like a very dull thud, you either have lost your air charge or you have a bladder issue. And if the tank has a bottom drain, you can close it off from the system and open up the drain and see how much water comes out. Don't be surprised if water comes out. It's common for water to condense in there. So like maybe a gallon or two of water can be in the bottom, but any more than that is going to be a leaking bladder, especially making sure that you have the expansion tank closed off to the system, because the entire bladder is just going to drain out of the leak. But depending on where the leak is, it may not always drain. So it'll be like 50-50. But if you have system water coming out the bottom drain of your bladder expansion tank, you have a bad bladder and it needs to be replaced. And when you replace the bladder, you will thank the installer who used the proper union and garden hose connection and ball valve to properly isolate the tank so that you don't have to get wet that day, and you can properly change out the tank and do all the service and keep the system online or not drain the entire system. So always pump away from the expansion tank from the point of no pressure change. Read Dan Holohan's Pumping Away book and or listen to the next episode of Boiler Wild. Dun, 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 dun. Thank you for listening. I hope you have a great day. If you haven't already, rate this podcast 5 stars and stay wild.